Okay. Okay, so I'm going to repeat it quickly. So sound intensity. Intensity is defined as the rate of sound energy flow per unit area or power per unit area. So let us start from power per unit area, P over A. So we know that P is also equals to work done per unit times or energy per unit time. Therefore, we can expand the equations into E over T divided by A. So the things that you have to be careful is the A in these equations, because the A in these equations, it represents area. Okay, it represents area. Whereas later on we'll look at another A, which is amplitude in this subtopic. So make sure you don't get confused between these two A. All right. So we have two A in this subtopic. First area, the second one is amplitude. So it is a scalar quantity, and the unit is watt, watt per meter square. Okay, watt per meter square. Why? Because a unit for power is watt, and then a unit for area is meter square. So when you use P divided by A, you will obtain Wm negative 2. So the shape of the sound wave, okay, sound wave, it travels in all directions. So even though you are facing maybe you're not facing me, you're facing your friends, okay, your back is facing me. So when I talk, when I speak, you can still hear my voice because sound is traveling in all direction. So we say the shape is a spherical shape, not circular shape. If you look at this a diagram, okay, the diagram in the square box, it looks like a circular wave. That is because you're looking at it on paper. On paper, you cannot sketch 3D wave. It would be quite impossible. Okay, that's why on paper, usually the shape that you see is a circular wave. But the fact, okay, in fact, what happens here is it's traveling out in all direction. It's a 3D, it's a sphere, okay, spherical shape. So this is quite a popular questions in your exam where it asks you what is the shape of the wave. So it's not a plane wave, it's not a circular wave, but it is a spherical wave. Okay, it's a sphere like a ball. So when I speak, when I talk, even you are standing behind me or on the left or on the right, you can still hear my voice. Okay, it doesn't matter where are you, as long as you're standing around me. Okay, you can still hear my voice because sound is traveling out in all direction. Okay, now this is the second A that I mentioned just now. You have amplitude. So intensity is directly proportional to the square of amplitude. So how do I know A is directly proportional to A squared? So let's go back to the equations for sound intensity. Sound intensity is equals to E over T divided by A. Okay, so this is the things that we see just now. Okay, the equations that we see just now. So if you look at the equations, what we learned in a previous subtopic, okay, in the chapter 9, so we know, okay, E is also, in the chapter 10, we know E is also equals to, now you're looking at particles, okay, you're looking at amplitudes of the wave, the particles, the oscillations of particles. If you remember, we say the amplitude, the oscillations of particle, it's a periodic motion. If it is a periodic motion, then the energy is 1 over 2 Ka squared. Okay, 1 over 2 Ka squared. Where this A, okay, the A's that we're looking at here is the amplitude. So in chapter 9, the A is amplitude. So now we have these equations. So based on the equations right here, okay, based on these equations, we know that I is directly proportional to E. Okay, and according to this equation, E is directly proportional to amplitude, right? So when you combine these two equations together, when you substitute E equals to 1 over 2 Ka squared into the equations, what we have right here is I is directly proportional to amplitude squared. Okay, amplitude squared. So that's why, okay, that's why here in your notes, it tells you intensity is directly proportional to the square of wave amplitude. That is because we combine these two equations together. Okay, we combine I equals to E divided by T over A, and then E at the same time is equals to 1 over 2 Ka squared. So basically, if you combine these two equations, you will have an equation that looks like this. I is equals to, okay, E, oh, no, not E. I substitute the equations into the equations. I have 1 over 2 Ka square divided by AT. You have these 2A in the same equations, but these 2A, they carry different meaning. The A here is the area, and then the A above is the amplitude. All right, so make sure you don't get confused between two different A. You have area and you have amplitude in the same equations, in the equations for intensity. So take notes, yeah? So intensity is directly proportional to the square of amplitude. That is because of these two equations. We combine these two equations. So the greater the amplitude means the more intense of the wave. Okay, the intensity is higher. So based on the equations above, okay, this is the graph that we have. Because we say I is directly proportional to A square. So when you sketch a graph of I against A square, you obtain a straight line. But when you sketch a graph of I against just A, you obtain a curved graph, okay, an exponential graph. So this is all based on the relationship. I is directly proportional to A square. Now, how about distance? Okay, so distance, the intensity of a sound decreases as you get further away from the source. Okay, so we say intensity is inversely proportional to the square of the distance from the source. Okay, why? How do I know? Now, again, we have I is equals to P over A. A is area. So you are looking at the area of a spherical shape. So A is equals to 4 pi r squared. Therefore, when you sub it into the equation, when you combine these two equations, you have I is equals to P over 4 pi r squared. Therefore, the relationship between I and R is I is inversely proportional to R squared. Okay, that's why we have I is inversely proportional to R squared. So the diagram here, it just shows you the relationship, okay, the relationship between I and R squared. So I'll leave it to you. So again, we are going to plot a graph. If you plot a graph of I against 1 over R squared, because the relationship is proportional, therefore you obtain a straight line. But if you just sketch I against R, then you're going to get a curved graph here. All right, so the graph, you sketch it based on the relationship. Okay, based on the relationship. Okay, so we are done with 10.3. 10.3 just tells you what is sound intensity and what is the things that affect sound intensity. Okay, what is the things that affect sound intensity? All right, so now next we are going to look at the applications of sound wave. So where can we find the sound wave? Right, yeah. Okay, so where can we find sound wave in a reality? Okay, so sound wave actually can be generated in under two different situations. The first one is on the string. When you plug a string, so where can you find this sound wave? A very typical example would be your guitar. Okay, if you play guitar, actually you are plugging the string. Okay, you plug the string and then it generates sound. All right. Before we proceed to the notes here, to the derivations, I wanted to write down the definitions for few terms. Okay, the definitions for this few terms. So these few terms, they are very important in your chapter 10, 10.4. All right. So I'm going to go through my own notes quickly, and I want you to write down something. Okay, so in musical instrument, the source of the sound is set into vibration by striking, by plucking, by bowings, or by blowings. So the standing wave, they are produced and the sound vibrate at a natural frequency. So the vibrating source in contact with air and it pushes the air to produce sound wave. That's why when you plug guitar, okay, the vibrations of the string, it vibrates the air particles around the string. And the particle, okay, the vibrations of particle will then be traveling towards all direction. Okay, and that's why you can hear the sound when you plug the guitar. So the vibrating source is in contact with the air, okay, or another medium. So you need a medium, okay, you need a medium to transform, okay, to what, to move the sound, okay, to move the sound towards you. So it pushes onto it and produce sound wave that travels, okay, so you need a medium so that the sound wave can travels out. Without medium, which means, for example, in vacuum, okay, you won't hear sound because there's no medium for particles to vibrate, for the sounds to travel. So you need a medium, okay, for it to travel. So the frequency of the wave, they are same as those of source, but the speed and the wavelength can be different. Okay, so you can have this different speed and different wavelength, but the frequency is fixed. So these three terms, I want you to write down the definition. You're going to see these three terms very, very often in the questions, and you need to know what is the difference between them. So what is a fundamental frequency? Fundamental frequency is the lowest resonant frequency. So in this chapter, we are going to focus on resonant frequency. Okay, resonant frequency, which is the frequency that gives you the highest frequency of sound. Okay, the highest sound, the largest sound. So fundamental frequency is the lowest resonant frequency of the vibrating object. Harmonic, okay, harmonic is the multiple of a fundamental frequency, and it must be a whole number. Okay, so it cannot be 1.5, it cannot be 1.3, it cannot be 2.7, it cannot be 3.4. It must be a whole number, 1, 2, 3, 4, 5, 6, 7, 8. So it is the multiple of fundamental frequency. Okay, so if it is same as the fundamental frequency, then the integer is 1. If it is twice the fundamental frequency, then the number is 2. Now, and then you have another terms called overtone. Overtone is a slightly different than harmonic. Okay, it is also the multiple of fundamental frequency. Okay, but then it is above fundamental frequency. Okay, it is any resonant frequency above fundamental frequency. Right, so it doesn't include for overtone. It does not. Okay, it does not include fundamental frequency. Okay, it does not include fundamental frequency. So that is the difference between overtone and harmonic. Overtone and harmonic, they might have same value. Okay, they might have same value, but they won't. For overtone, it does not include fundamental frequency, right? So I give you some times, maybe 3 minutes to write down these three definition. Okay, 3 minutes for you to write down these three definition. It's very important. All right, it's very important. You need to understand the meaning. Okay, so write it down in your notes, yeah. Put it in your notes so that you can always see it and make sure you understand the difference.
Madam,
Yes.
can I ask why would the speed and wavelength be different as the source of the wave?
Why the speed and wavelength can be different? So the frequency of the wave, they are same as those of the source, but the speed, is equals to, yeah, so we have equations. V is equals to F lambda. So the things that affects your V and a wavelength, okay, because the frequency is always fixed, you're generating from same source. So if you're same source, then the frequency won't change. So V is directly proportional to wavelength. So we look at it in terms of the, in terms of relationship, okay, in terms of equations. And sometimes when you have two different objects together, okay, for example, now if you generate a source, okay, let's say now you have a tube, okay, you're looking at it in a different medium. Actually, we say V and wavelength, they are being affected by medium. So now let's say I'm going to plug a string, okay, this is a string. I plug the string, I generate a frequency F, let's say equals to 100 hertz, 10 hertz. Okay, not enough space for me to write 100. So let's say now I plug the string, I generate 10 hertz of sound here. This 10 hertz of sound is traveling in the string. Okay, so if it's traveling in the string, it will have a different set of V and lambda. But when this sound, okay, because it vibrates the air beside it, all these particles, they will vibrate with a 10 hertz as well. So when you're looking at this 10 hertz now, okay, the particles inside the tube, they will then have a different set of V and lambda. But they are still moving, they are still having the frequency of 10 hertz. But the things that change is the V and lambda. You're looking at different medium, you're looking at the different situations. So V and lambda, they will have a different value than your F. Is that okay?
Yeah, that makes sense.
Okay.
Thanks, madam.
So you will see the much better, much clearer when we go through the derivations, because you look at the derivations of velocity and the wavelength in a string, and also you will see the velocity and also the wavelength in the air column, okay, like the one that I showed you just now. All right. So for the derivations, okay, actually I would prefer to use my own notes, okay, rather than your notes here. But still, I will give you the value after this. All right. So for derivations, I'm going to use my own notes. Okay, I'm not going to use your notes. So first of all, we are going to see how to derive the equations. First, we are going to see when you plug the string, okay, there are quite a lot of possibility. If you plug the strings and you got a wave that as shown in the first figure, then you will have something called the fundamental, okay, the fundamental frequency. You plug it, it just gives you one string, okay, you have only one, okay, now how am I going to say it? Let's say you have a 2n, okay, this 2 fixed n. This 2 fixed n is definitely notes, the notes of the wave. So if you remember the things that we see in a standing wave, all right, no, I'm not going to sketch the y and x axis. So we have this wave, okay, so this is the equilibrium position, and then another wave in the opposite direction, okay. So two waves, when they superimpose with each other, this is what we obtain. And the place where they experience total cancellation, this is what we call node, all right, if you remember. So NT node is the maximum position, it's the amplitude, all right, NT node is the amplitude of the standing wave. So what we're going to look at right here is actually what happens in the standing wave. So when you plug the string, okay, when you plug the string, what actually happened is you are generating an incident wave, okay. You look at the diagram above the table first. So you are generating an incident wave, you create a wave in the string, and when string hits the fixed end, okay, the wave being reflected, all right, the wave being reflected. So you're looking at what happens within the same length L. So this is the concept that we're going to use in our derivation. If you plug the string and then when it reflected, it gives you a shape as shown in the first figure in the table. Then we say what? What can we say about this wave? We say this L is now equals to lambda over 2. It gives you only half cycle. Okay, so when you compare to the shape on the on the right hand side, the shape for the first figure is actually just the first half cycle. All right, the red color cycle. So in this case, this is only half wavelength, not the full wavelength yet. That's why we say between this L, between the lengths given, we have only half wavelength. Therefore, the relationship between L and wavelength is L equals to lambda over 2. Okay, the first table here. Okay, the first equations in the table. So we look at what happens between two fixed end. For example, in a guitar, when you plug it, if it only returns, give you back a half cycle, then we say L is equal to lambda over 2. So in this case, we call it fundamental frequency, okay, or first harmonic, because remember, harmonic is the multiple of fundamental frequency. So first harmonic is definitely equal to fundamental frequency, all right? So when you're given fundamental frequency, the numbering for harmonic is equal to 1. And then the second thing, now if you plug the string, okay, you're not plug it at the middle right now. Now you plug it at somewhere here. Okay, you plug the string at somewhere here. This is U, and then now you plug the string here. Okay, you plug the string here. So if you plug the string at somewhere that is not at the middle, maybe you now obtain the second diagram. Okay, where if you look at what happens between two fixed end, okay, now we still have the two fixed end. So what happens between these two fixed end now? Now you have one complete cycle. In this case, we say now your L is equal to the length of the lambda. Okay, lambda is equal to the length L. Because now you have one complete cycle in between two fixed end. So in this case, we call it first overtone, okay, or now second harmonic. It is the resonant frequency above your fundamental frequency, right? The resonant frequency above your fundamental frequency. That's why we call it overtone right now. So this is your second second resonant frequency. That's why we call it first overtone or second harmonic. Okay, second harmonic. Now, if you change the positions that you plug again, okay, you plug it at the different positions again, then what is going to happen? Maybe you create another, okay, you generate another wave in between the shape. You generate another shape in between two fixed end. If you look at this diagram right now, what happens right here is now you have, okay, one wavelength, okay, 1 lambda, and you have another addition 0.5 lambda. Okay, so which means what happened right now, still in between the same fixed end. Okay, you are still plugging the string on the same guitar, but now because of the positions that you're plugging, okay, now you have 1.5 wavelength in between two fixed end. So this is our second overtone or third harmonic. So the relationship now we say is L equals to 3/2 wavelength. So when you compare these three equations, okay, L equals to lambda is actually L equals to 2/2 lambda. Okay, I'm going to change it so that they all have the same denominator. So now you have L equals to lambda over 2, L equals to 2/2 lambda, L equals to 3/2 lambda. If you keep going on, then you'll have L equals to 4/2 lambda, L equals to 5/2 lambda. Therefore, the general relationship between L and lambda in a string is L equals to n lambda over 2. Okay, L equals to n lambda over 2. So from here, okay, from here, we can then determine the velocity and the frequency of the frequency, okay, of the frequency that is not fundamental frequency. Okay, so harmonic. So I'm going to put a harmonic and overtone in this table. So first harmonic, we use value n equals to 1. Okay, we use the numberings for harmonic. So when it comes to calculation, okay, the very important thing is here, the numbers of n, because this is the equations that we're going to use. This is the value that we're going to use in our equations here, right? So numbers n, we follow the numbers of harmonic. So if you're given overtone, then make sure you know. First overtone is equal to which harmonic? Second overtone is equal to which harmonic, right? Okay, so we have L equals to n lambda over 2. The general equations for wave is V equals to F lambda, regardless of the medium. Okay, this one, it can be used, okay, can be used in all types of medium. Okay, all types of medium. So it doesn't matter whether you're looking at strings, you're looking at air particles, or maybe inside the other items. All right. The V equals to F lambda is the general frequency. But if you're looking at strings, we are going to go into a more precise equations, okay, a more general equation, a more how to say, more specific equations, okay. The wave only for string, then we calculate the velocity by using square root T over mu. Well, it depends on the tension, okay. This is the tension. It depends on the force that you use to plug the string. So different force that you use, then it will have a different velocity. So this is a more specific equation that can only be used in string. So general equations for wave, we have V equals to F lambda. If you're looking at the wave that only happens in the string, then we have V equals to square root T over mu, where mu is M over L. This M over L is more on the property of the string. Okay, it is the mass of the string divided over the length of the string that you use. So mass over length. So velocity inside string, okay, the specific on the string, we look at the tension that you use, the force that you apply, and also the property of the string, the mass and the length of the string. So, well, it makes sense because now you're going to focus on what happens inside a string only. So V at the same time is equal to square root T over mu, and mu can be calculated by using M over L. So when you combine these two equations together, okay, when you you combine these four equations together, it then gives you a general equation for frequency, resonant frequency inside a string, where Fn is equal to n over 2L square root T over mu. All right, so you combine these four equations together, you go through a series of derivation. So F lambda equals to square root T over mu. F lambda is then equals to T over M over L, and then you keep deriving. Okay, you have what? You have a F equals to 1 over lambda square root, okay, T over ML, and then you keep deriving it, okay? So you keep deriving it, and eventually, I think they didn't derive mu. Okay, and eventually you obtain the equations. Okay, let me redo it again for you. Okay, so you keep the mu. I think you keep the mu in the equation. So you keep the mu in the equations, you derive it. So just now we have L equals to n lambda over 2. So lambda equals to 2L over n. So you sub it into the equations. Okay, so F equals to 1 over lambda T over mu, and then F is then equals to n over 2L square root T over mu. So this is how you obtain the equation. By combining three equations, okay, combine equations 1, equations 2, equations 3, then you obtain the general equation for you to calculate the resonant frequency in a string. So Fn equals to n over 2L square root T over mu. And at the same time, S is also equals to NF1. Okay, NF1. So this is the equation, all right? The equations for you to calculate resonant frequency, you have two different methods. Either you use F equals to n over 2L square root T over mu, or F equals to NF1, which is times your fundamental frequency. So it makes sense because you're looking at harmonic frequency, okay, harmonic. So you look at which harmonic you're looking at. So you just times the multiple. So now we have two equations that can be used to calculate resonant frequency in a string, all right? So this one is not in your notes. If you want, you can write it down. Your notes, they skip all this derivation. Straight away, they give you the equations only, okay? If you look at your handout, okay, your lecture notes, what you have right here, straight away, they give you the equation. Okay, they give you L equals to lambda over 2, lambda equals to 2L. And then lambda equals to L equals to 3 lambda over 2, lambda equals to 2L over 3. And then here you have V equals to F lambda Okay, F1 equals to V over lambda 1. F1 equals to V over 2L. So it keeps doing it for all of them. All right, so for me, this one is a less obvious. Okay, you can see what happens actually. So F2 equals to V over L, and then F3 equals to V over lambda 3. F3 equals to 3V over 2L. So this is what is given in your lecture notes. Okay, and straight away they give you the equation. V equals to square root T over mu, and the general equations Fn is equals to N over 2L square root T over mu, which is then equals to NF1. So this is the things given in your lecture notes. Okay, if you want to write it down, you may write it down. I give you 2 minutes to complete the blank first. All right, then I will give you another 2 minutes to copy the notes that I give you just now. Okay, that I wrote just now. So you fill in the blank first. Okay, you fill in the blank first. So the reasons why I use my own notes, because your notes, it doesn't show you how to obtain the equations. And you need to know the process, because sometimes question won't just ask for the final answer. All right, when it comes to application, the questions that they ask always is quite tricky. Okay, it's always quite tricky. You need to know what does it mean by harmonic, what does it mean by overtone. You need to know their relationship. Okay, and sometimes you might need to use some of the equations in the derivations in order to get the answer. Okay, in order to get the answer. So I give you two minutes to complete your notes first, and then 2 minutes to copy the additional notes. All right, to write down the additional notes. Kenapa tiba-tiba? Yes, any questions? Okay, so I will let you, I give you some time to write down the additional notes. Okay, so this is how I derive it, and the relationship between your harmonic and also your overtone. So make sure you know how to select N. Okay, how to select N. So once you understand this one, then the next two would be very simple. Okay, the next two would be very simple. All right. Okay, next. So the next is the examples in air column. Okay, in air column. So air column, for example, the instruments that you use is the fluid. Okay, fluid, you blow it, then the sound comes out. Okay, comes out from the fluid. Okay, so for air column, we are going to look at two different types of air column. One is open end, open at both end. Okay, if the question say open end, then it's open at both end. If question say close end, that means one end is being closed. Okay, one closed end. So now when you have an open end air column, both end they must be antinode. Okay, because they have less pressure in it. Okay, both end they are wide open, less pressure. Therefore, both end they must be antinode. Okay, both end must be antinode. So for the first one, for the fundamental frequency, the shape that you have is, for example, as shown in the diagram. Now this one, when you compare with the wave, okay, now let's see. If I have, this is the equilibrium line. Now my wave start from maximum. Okay, go to here, and then it goes back up again. And then the shape of another wave from negative, go to go to the positive. So this is a standing wave in the general situations, okay, in most of the situations. So what we have right here, if you look at the figures given in the table, it gives you from positive nodes to negative nodes. So which means you're looking at this side of the wave. So this side of the wave, this length is also represent half wavelength. Okay, it's also represent half wavelength because from here to here, this is one wavelength. And the part that we are looking at right now in the first figure is wavelength over 2. So it's half wavelength. Therefore, we say the relationship between L and the wavelength once again is equals to L equals to lambda over 2. Right? It's L equals to lambda over 2. So from antinodes to antinodes, we have half lambda in between the same length. So this one we call fundamental frequency or first harmonic. For first overtone or a second harmonic, in order to obtain the second resonant frequency, where how you can obtain note and note on both ends, well, you're looking at the full cycle now. Okay, so now you have lambda over 2. So both ends must be both ends must be open. Okay, must be antinode. So you try from the shortest distance, okay, shortest wavelength, where it give you both A, and then you go to the second stage where it give you A again, and then the third stage it give you another A and A. That is how we obtain the resonant frequency. Okay, as long as it fulfill the condition, antinode and antinode on both ends. Right? So kamu tengok wave, kamu punya sound wave, it will just keep traveling. Okay, if you have a sound wave, it will just keep going on. Okay, if you have a wave, then it will just keep going on. Then the things that we use to identify to sketch the wave is actually the relationship. Now for open-end pipe, both end must be antinode and antinode. So you look at, okay, the first part that they give you antinode and antinode is half wavelength. Okay, and then the second part where it give you antinode and antinode is one wavelength. And then where it give you antinode and again, 3/2 wavelength. Okay, so basically this is what we obtain in the diagram. So this is your first first resonant frequency. Okay, first resonant frequency. Second resonant frequency. And then a third resonant frequency. And then it will just keep going on. So for an air column, actually you can have a lot of resonant frequency. All right, depends on the lengths that you're looking at. Different lengths, okay, you will have a frequency, different resonant frequency. So the first overtone or the second harmonic, the second resonant frequency, now you have L is equals to lambda. It happens at one wavelength. And then for the next resonant frequency, the second overtone within the same length, okay, so you have A again. Okay, again, you want it to go back to antinode. Therefore, if you look at the graph just now, you look at the wave just now, the next time where you obtain antinode, okay, it happens at 3/2 lambda. Okay, this is over 3/2 lambda. This is lambda. So 3/2 lambda. So you put 3/2 lambda within the same length. This is your third harmonic. Okay, your second overtone. So antinote and antinote again on both end. Okay, antinote and antinote again on both end. And now we know the relationship is L equals to 3 over 2 lambda. This is for open end. Open end, the relationship between L and lambda is very similar to the string. Okay, L is still 2 over 2 lambda. So you look at the general relationship. If it keeps going on, then again, the general relationship between L and wavelength is L equals to n lambda over 2. Okay, L equals to n lambda over 2. So the wave velocity in a general equation is V equals to F lambda, where V is now the speed of sound in air. Now, why I don't have a specific equation for air column? Because V, okay, the speed of sound in the air is a fixed value. Okay, it's a constant value. I think it's a 343 meter per second. But it depends on books. Some books they give you 344, some books they give you 345, 346. All right, in exam they will give you the value. Therefore, we don't have a specific equation for the velocity of the sound traveling in the air. Just now the velocity is for the uh particles in string. Okay, this one is for the particle in string. So now for the particles in the air, you don't have a specific equations. Why? Because they have a constant value. So now we have just V equals to F lambda. Therefore, when you sub equations 1 into equations 2, you obtain F equals to NV over 2L. So this is the equation for open-end air column. Okay, this is the equation for open-end air column. Very simple. You identify the relationship between L and lambda. From there, you sub it into V equals to lambda, and then you obtain the general equation. Okay, you obtain the general equations. So basically what we're going to look at, we look at in between two fixed end, what is the shape of the graph that you have? Okay, what is the shape of the graph that you have? Whether you have a first resonant frequency, second resonant frequency, third resonant frequency, and so on. Okay, so that one, you use it N to represent the numbering. Okay, to represent the frequency that you are looking at. So again, N is equals to 1, 2, 3, and so on. Okay, 1, 2, 3, and so on. So this is the open-end air column. So again, I give you a few minutes to write it down. In your lecture notes, okay, in your lecture notes, I think they just look at the final equations only. Okay, they just give you the final equations. Let's go back to your notes for a while. Okay, so in your lecture notes, they give you the equations here. Fn equals to NV over 2L equals to NF1. Okay, so Fn equals to NF1 basically can be used in any equation because it just tells you the relationship between resonant frequency and fundamental frequency. Okay, so basically this part is the harmonic. And then this part is the multiple, this part is the harmonic. And then this one is N times fundamental frequency. Okay, fundamental frequency. And then for closed N, give you Fn equals to NV over 4L equals to NF1. So this is in your books. Okay, this is the things in your books. Okay. So I give you 1 minute to write it down. Okay, to write down the table, to write down the relationship. You can snap a picture, also can. It's up to you. So the most important thing is the relationship. Once you know the relationship, then you will be able to derive the equations for all three different situations. Okay, for all three different situations. Okay, so next one. So next one is a closed-end air column. Closed-end air column, the typical example is a clarinet. Okay, clarinet. So you can find a closed-end air column inside it. Okay, inside the musical instrument, clarinet. So for a closed-end air column, there's always a note at the closed end because of the air pressure. Okay, because this one, the closed end, it's always a note. Okay, whereas the open end, the air can move freely. That's why you have an anti-note. So for closed-end air column, we only have odd harmonic. Okay, we don't have even numbers harmonic, right? That one you can only see it through value. So unfortunately, I don't have the value with me right now. Okay, so I can only tell you the idea, the concept. So for closed-end air column, we have only odd harmonic, right? Because remember, harmonic is the multiple of fundamental frequency. Okay, for fundamental frequency. So above fundamental frequency, maybe it's a 3 times of the fundamental frequency, but that one is only your first overtone, your second resonant frequency. Okay, the values of second resonant frequency is 3 times of your fundamental. So that one, okay, that one we cannot do anything. So right now, let's see. Okay, so for closed-end air column, because now you need a notes here and an anti-note. So again, if you start from a standing wave, now this is against your equilibrium position. So this is your standing wave, right? And then this is a reflected wave. Okay, so you blow the instrument, it generates a wave, and then it's being reflected by closed end. So now what we want the shape that gives us a note and anti-note. Okay, the shortest length that gives us a note and anti-note. So if you look at this diagram, now what we have right here, this is a note, 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 ups. Okay, and then we have an anti-note here. Anti-note, 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 anti-note. So the shortest length that can give us a note and anti-note is here. Start from here right up to here only. So based on the diagram, this is only 1/4 wavelength. So now you move this yellow color part into our closed-end air column. That's why you obtain the first diagram here. Okay, you obtain the first shapes here. So the relationship between the length and L is now L is just equal to lambda over 4, right? Because this is only 1/4 wavelength. And this one, we call it fundamental frequency or first harmonic. Okay, first harmonic. And then the second one, okay, the second length that will give you 1 note and 1 anti-note. Let's go back to the diagram again. Now you start from notes here, and then you are going to look at the following anti-note. The next anti-note would be here. Okay, so therefore, based on the diagram, okay, the second times that I can obtain 1 note and 1 anti-note is when it happens at 3/4 wavelength. Okay, kali kedua yang saya boleh dapat satu note di hujung dan satu anti-note di satu hujung lagi adalah apabila lambda sama dengan 3/4 wavelength. Dia punya wavelength sama dengan 3/4 lambda. Okay, so kita tengok, okay, we compare the general shape and then we just crop it and then put it into our closed-end air column. That's why now we have a shape where L is equal to 3/4 lambda, right? This is the second times where we can obtain note at one end and anti-note at the other end, right? So kita nak cari shape yang boleh bagi kita note dengan anti-note di hujung, satu hujung dan satu hujung lagi. So this one, okay, this is the second resonant frequency. So second resonant frequency, we call it first overtone, right? But if you look at the value, now it is 3 times, the value is 3 times of the fundamental frequency. That's why we call it third harmonic. Okay, that's why we call it third harmonic. It's 3 times. So the second times where you obtain the overtone, it is 3 times of your first harmonic, right? So maybe fundamental frequency is 10 hertz, and then your second resonant frequency is 30 hertz. Okay, it's 30 hertz. So this one is 3/4 of your fundamental frequency. That's why we call it third harmonic. Right? We call it third harmonic. And then the following one, okay, let's say now it happens at 50 hertz. So this 50 hertz, it gives you 5 times of the fundamental frequency. That's why we call it fifth harmonic. But this is just your third resonant frequency, the third times that you can obtain the resonant frequency. So this is your second overtone. Okay, your second overtone, your third resonant frequency. But now it's 5 times of your fundamental. That's why we call it fifth harmonic. So in your closed end air column, okay, we don't have a so-called even number harmonic. So keep that in your mind. It's very important. All right, it's very important. So for closed end air column, this phrase, okay, this phrase is very important. You only have odd harmonic. So based on the diagram, we obtain a set of relationship for L and lambda. So for first harmonic, L is equals to lambda over 4. Third harmonic, L is equals to 3/4 lambda. Fifth harmonic, L is equals to 5/4 lambda. So the general equations, if you look at here, okay, this is your 1 lambda over 4, 3 lambda over 4, 5 lambda over 4. So the general relationship is L equals to n lambda over 4. Okay, n is the numbers of harmonic, is now equals to 1, 3, 5, which makes sense because based on our derivations in diagram, we have 1 lambda, 3 lambda, and 5 lambda, 1, 3, 5. So now you have n lambda here. Okay, so L is equals to n lambda, but now it's over 4. Just now for open end air column is L equals to n lambda over 2. For closed end air column is L equals to n lambda over 4. Again, the general equation is V equals to F lambda, where V is the speed of sound in the air. So again, you're looking at the speed of sound in the air. Therefore, it is a constant value. There's no specific equations. Okay, so when you combine all them together, you obtain a new equation called Fn equals to Nv over 4L equals to Nf1. So this is the general equation for closed end air column or closed end pipe. Okay, or closed at one end. That is the terms that you will see in question. Closed at one end, closed end air column, closed end pipe. Okay, so this is how you derive it. So basically, we are done with application. So basically, we are going to look at just the 3 applications. The first one is what happened in a string. The second one is what happened in an open end air column. And then the third one is what happened in a closed end air column. Okay, so in exam, in case you forgot about the shape, okay, you can try the things that I show you just now. All right, even though it's not a very correct idea, but at least you know what is the shape of the graph that you have to put in the diagram, in the figure. All right, so if you're looking at the first harmonic, then you look at the first time you can obtain a note and antinote in a diagram. You look at the second harmonic, okay, so this is the first time. So we call it, we use it for the shape for first harmonic. This is the second times where we can obtain a note and antinote. So this is the shape of the wave that you should put in the closed end pipe for second harmonic. Okay, for the third resonant frequency or for your fifth harmonic. Okay, so this is the third times where I can get, N and A in a standing wave. Okay, this is for the third time. So I put it in the second overtone, the third resonant frequency, which is your fifth harmonic in the diagram. Okay, so you just crop the shape and then you put it in this closed end pipe. So why I say you need to know how to sketch the shape? Because almost every application questions, they start from sketch the standing wave for a given situation, okay, based on the questions given. So you will see in the questions in your tutorial, all right? First questions, usually they ask you to sketch the wave fronts for the stationary wave. And this is the wave, okay? The figure is the things that you need to sketch, all right? Figure is the things that you need to sketch. Okay, now let me go through the summary quickly. Okay, kita pergi kepada summary secara cepat. So applications, we have 3 types of application. Okay, we have 3 types of application. The first one is a string. Okay, the first one is string. Where strings, you have 2 notes on fixed end. So you have a nodes here, and then you have a nodes here. So you just look for the shape that will give you nodes in between this length. Okay, so this is a length, and then the shape is up to you. Okay, you look at which resonant frequency that you are looking at. Okay, you are going to sketch which resonant frequency. You are going to sketch which overtone, which harmonic. Okay, then you put the shape in here. And then the equations, we have two equations for velocity. The first equation is the general equation, and the second equation is the velocity for the particle in the string. V equals to T over mu. So when you combine them together, you obtain the general equation called F equals to N over 2L square root T over mu. This is the general equation. Okay, this is the general equations. Of course, you have another general equations which can be used in all sort of situation. F equals to NF1. Okay, regardless of which applications you are looking at. And then the second applications that we look at today, okay, is a open end. Okay, open end air column. So what is the things that is important about open end air column? You have NT node on both end. Okay, NT node and NT node on both end. And then for the equations, you have only V equals to F lambda. Okay, because V sound is a constant value. Okay, V sound is a constant value. And it will be given in the questions. So from here, you then derive the equations. Okay, you then derive the equations. F equals to NV over 2L. Okay, this is the equations that can only be used in open-end air column. So it is unlike the general equation. Okay, the general equations can be used in all sort of a situation. All right. Oh yeah, and of course you have to know the relationship between N and L. L and lambda, sorry. Okay, you have to know the relationship between L and lambda. And the third one that we look at today is a closed-end air column. All right, closed-end air column. So the important things about closed-end air column is now, okay, you have one node and one NT node. So three different applications, you have three different situations. Nodes, NT node, NT node, nodes and NT node. Okay, again, the V is just equals to F lambda because V sound is constant. So we don't have a specific equation for the velocity in air column. And then we have F equals to NV over 4L. So this is the equations that can only be used in a closed-end air column. And the important things for this closed-end air column, N is just odd number. Okay, you have only odd numbers in your closed-end air column. So this sum up everything in 10.4. Right? So I give you a 3 minutes, 3 minutes to write it down. So 15 past 12, I will continue again with the last subtopic, which is the droplet effect. Okay, droplet effect. So droplet effect is just a very short and simple subtopic. I can finish it within 15 minutes. All right. So 3 minutes for you to write it down, the summary. All right. Of course, you can add in more information that can help you to understand the situations much better. Okay, so I hope you guys can understand, yeah. The most important thing in this subtopic actually is how to sketch the figure. Okay, if you understand how to sketch the figure, then you should be able to obtain the equations in your exam. So it's not very hard. Okay, actually it's not very hard. Don't be afraid of this topic. Quite a lot of students, they don't like to study this topic because they think it's very difficult. Okay, but this topic, it gives you the most score in your exam. Okay, so now let us go back to your notes again. Okay, your lecture notes. So your lecture notes basically it just give you this one. Okay, these two equations. All right. Now let us continue with a Doppler effect. So now we are done with the instrument that is not moving, the sound wave that is not moving. So 10.3, we look at what is a sound wave. Okay, so sound wave is a wave that is traveling. You need a source, you need a medium. So the source generates sound and the medium, okay, you use it to travel, the sound travels through the medium. Okay, the medium is being used to travel. And then in a 10.4, we look at what happened. Okay, what happens in the musical instruments where your source, your sound wave, they are not moving. Okay, you just plug it, you blow it, and then they generate sound wave. And after it's being reflected, it gives you a stationary wave. And from there, we deduce the shape of the wave. And then we deduce what is the equations that can be used to find out what is the frequency, what is the resonant frequency in the musical instruments given. And this chapter we're going to look at, this chapter we're going to look at, what happened is now you have a moving sound wave. Rather than the wave that is not moving, now we want to look at the wave that is moving. Okay, the sound, the source that is moving. So Doppler effect is defined as the change in the apparent frequency of a wave as a result of a relative motion between the source and the observer. So apparent frequency is the observed frequency. Okay, the things apparent is the observed frequency. We use it to refer to the observed frequency. So pitch is defined as the properties of sound characterize the highness or lowest or lowness of the tone of an observer. So intensity, we look at loudness. Pitch, we look at the sharpness of the tone. So it varies with frequency of the sound wave by using the following relationship. Higher frequency give you higher pitch. Okay, so frequency give you pitch, intensity give you loudness. Highest intensity means louder the sound. So if pitch increases, hence frequency also increases, but wavelength will decrease. Okay, wavelength will decrease because the wavelength is inversely proportional to f. Okay, you have a v equals to f lambda. So if your object is traveling with constant velocity, then v and f and lambda, they are inversely proportional to each other. So explanations of Doppler effect. So if your object is at rest, then you will have a spherical shape of the wave that is nice. Okay, that is distribute evenly on both sides, on all direction. Actually, not just both sides. Front, back, up, down, they are all have a same distance. Okay, so you look at here, the wavelength is the same. All right, they have the same wavelength in front and at the back of the object. If your object is moving to the right-hand side, what actually happened is it squeezed the wavelength on the right-hand side. Therefore, the one on the right-hand side and the one on the left-hand side, they look different now. This one is being compressed, okay, because it's moving towards the right-hand side, but then the one at the back is being stretched. Okay, you pull the wavelength. So now you have a larger wavelength behind the object. Okay, so compress and stretch. Therefore, you will receive different wavelength or different frequency, the observer. So the first one, observer A and B, they will hear the same pitch. They will have the same pitch. They will hear the same noise. For the second one, when the track is moving, observer B will receive a higher pitch compared to observer A. Okay, the pitch received by observer A is a smaller. All right. So consider the siren of a fire truck is at rest. Okay, so this one I just done explaining it. So when the truck is moving, the wave fronts it moves forward, they are closer to each other because they are being compressed. This is because the fire truck as it moves is chasing the previously emitted wavefront. Okay, and therefore they get closer. So the observer on the sidewalk in front of the truck, which is observer B, the frequency hertz is higher. The wavefront emitted behind the truck is farther apart, okay, because it's running away from the previous wavelength. Therefore, observer A will observe a lower frequency. okay, a lower frequency. So the general equations that we use to look at the frequency received by the observer above is a F naught equals to V plus minus V naught over V minus plus Vs. Okay, V minus plus Vs. And then this is your Fs. Well, you can still write plus minus, okay? Plus minus minus plus, actually it doesn't matter. Just make sure you have the right subscript, because in this one equation, you have 3 different speed and 2 different frequency in one equation. So V without subscript is the speed of sound, which is a constant value, okay, which is a constant value. Vs is the speed of source if it is moving. Vo is the speed of observer. Fo is the observed frequency, okay, the frequency received by observer. And then Fs is the true frequency, or we say the frequency from the source. Okay, so this is from source, generated by the source, most probably a siren. And then this is the frequency received by observer. Okay, so most probably it's you. All right, you are the one that listens to the sound that is being emitted by the siren. So you are the observer. The one that you hear, you listen, is the observed frequency or apparent frequency. Okay, or apparent frequency. Okay, so now let's say if you have a stationary observer. So for instance, stationary observer, your VO is equals to 0. Okay, 0 meter per second, because observer is not moving. Okay, so stationary observer moving towards the source. Okay, as the source moving towards the observer, sorry. So stationary observer, moving source. Okay, moving source. So now your source is moving towards the observer. Let's see how are we going to generate it. How are we going to form the equation? So the equations that we use here, observed frequency is equals to, now your VO, okay, your VO is 0. So well, we just have, oops. Okay, wait, yeah. So we have just a V. Okay, we have just V here because now your, wait, yeah, it's hang. Okay, so we just have V right here because your VO is now equals to 0. Okay, so divide by V. Annoying. Okay, divide by V. Well, if you look at the equation just now, you have V plus minus Vs. So which V are you going to use? Okay, plus or minus sign. So Vs is in the same directions as your V. So we use a minus sign. So if you use common sense, actually you can still obtain a minus sign here. Why? Because when the sound moves towards you, you're not moving, the sound moves towards you, then your Fo should be greater than your Fs, which means this one, it should become smaller. Okay, the denominator should become smaller. Okay, the denominator. The V minus Vs should become smaller. Okay, it should give you a smaller value here in order to obtain a higher F naught. Right? If the source moves towards you, then Fo must be greater than Fs. So V should minus Vs in order to give you a higher Fo. Okay, observed frequency. So another way that we use to determine whether we should use a positive sign or a negative sign, you look at directions of Vs and V. Now, Vs is very simple. Vs is the directions of the source. If the source moves towards the right-hand side, then the direction is to the right. If the source moves towards the left-hand side, then the direction is to the left-hand side. Then how about source? Now, it's very simple. The direction of V is always from source to observer. Okay, this is always from source to observer. Regardless of the directions of motion, your source can move to the left, can move to the right. It doesn't matter. But if you look at the diagram here, now your source is on the right-hand side and observer is on the left. Therefore, the V is traveling from source to observer. That's why your V is going to the left-hand side, regardless of the motion. Okay, even if your source is moving away, you look at the one on the right-hand side, your V is still going to the left because it's always from source to observer. Okay, dia tak kisah. Even your Vs is now going to the right, but V is still going to the left. Okay, V is still going to the left. V is not being affected by anything. It's always from source to observer. So if they are pointing towards the same direction, then you use a negative sign in your equation. If they are pointing towards opposite direction, then the equations will just be equals to V over V plus Vs right now. Okay, and then Fs. So by using a plus sign, it will give you Fs greater than Fo, which makes sense because now your source is moving away. So the pitch that you receive, of course, is reducing because the object is getting further away from you. All right, so frequency is decreased. So Fo, observed frequency, is less than the actual frequency. Okay, the frequency that you observe is less than the actual frequency. So Vs and V, they are in the opposite direction. That's why you use the plus sign in your equation. Okay, you use a plus sign in your equations. Okay, next one. Next case, now you have a stationary source. Source is not moving, but now we have a moving observer. So source is not moving, our Vs is now equals to 0. Okay, 0 ms negative 1. So in your syllabus, we will have either 2 not moving object or 1 moving object. Okay, object moving or siren moving. So in your syllabus, we are not looking at 2 moving object. Okay, we are not looking at moving observer, moving source. No. Okay, dalam syllabus anda, kita cuma tengok either one is moving. Okay, either one is moving. Okay, now you have Vs equals to 0. So the equation F naught is now equals to, well, at the bottom, we just have V right now. Okay, because now our Vs is equals to 0. So what are we going to do with the VO part? Okay, we have V and VO. Should we use a plus or minus sign? Now, you are moving towards the source. Of course, the sound will get higher. Therefore, we use a plus sign here. Okay, because you want to get a, oh, I used the wrong subscript, sorry. The subscript should be S. Okay, because now we want to have a higher FO. Okay, so we need to use a plus sign here in order to get a larger FO. Okay, to get a larger value. So V is in the opposite directions with V. Okay, VO and V and they're in the opposite direction. Therefore, we use a plus sign. So again, this V, it does not depend on the motion. Okay, it just look at the position of the source and the position of the observer. The directions of V is always from source to observer. All right, from source towards observer. So you need to know how to determine the direction. So if observer is moved towards source, means your VO and V, they are in the opposite direction. Opposite direction, you use positive sign. Same direction, again, you use negative sign. So V minus VO divided by V, Fs. Okay, Fs. So this is the rules, all right? So the rules is very simple. If your Vs and VO, okay, they are in the same direction, with V, then we use a negative sign. All right? If your Vs and so if your Vs and VO is in the opposite direction with a V, then you use a plus sign. Okay, you use a plus sign in your calculations. So that is how we solve it. Okay, that is the rules. Okay, I'm going to call it rules. The rules that we use to choose the sign convention, whether you want to use a plus sign or you want to use a minus sign in your calculation. Right? So done. Okay, that marks the end of chapter 10. But before that, I want you to write down something. Okay, I want you to write down the graph. Actually, there should be one graph in your notes. Okay, so this one. Okay, I want you to write it down. So the following graph apply for stationary observer. So if let's say you're standing at the roadside, okay, and then an ambulance walk past you. So what happens to the frequency? So if you're observer, if you're standing right here, not moving, this is you. So if it moves towards you, then part A, you have a higher frequency, higher observed frequency, because now the ambulance is moving towards you. When it is just right beside you at part B, the sounds that you receive, the frequency that you receive is equal. Okay, it's the same. Okay, and then if it walked past you, it moved away from you, then it will become part C, where your F note is now less than Fs, the source. Okay, so from positive R towards negative R. Okay, from in front of you until behind you. So this is the frequency that you're going to receive. Okay, so you need to know how to sketch this graph, okay? Because sometimes you'll be given a graph, it asks you to interpret it, or maybe the question will ask you to sketch a graph and it asks you to label the value, all right? Something like that. So you need to know how to sketch the graph. So it's applied for a stationary observer. So let's say now you have a car, an ambulance with a siren, okay, with a siren. So moving from positive R towards negative R. So this is what happens to the frequency that you're going to receive. All right, so I give you a few minutes to write it down. All right, so we are done. Okay, basically we are done. So if you are done writing it down, then you may leave the class. Okay, if no question. So yeah, that's all for today. Thank you for attending today's class.